منصف غادي قدام لا هذيك دير انت هادي بحال هكا كنظن شوف غادي تجي لهنا شوف دابا ولكن هذاك تسمع الصوت من عندك خاصك تبدا تقول Okay, this one is yours. Hello? Hello? Hi? Okay. Test. I see the test, 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 test. Can you go there and check what is working? Yes. Right? And then you go there and check if the YouTube link is working. Okay. Hi. Hello. Hi. Hello. Is everything working fine? Okay, seems to be. Safi, okay. Parte quando vedo il birro, parte quando vedo il birro di lube.
Easy one.
Hello, this is a test. Is everything working well? Hi. 1, 2, 3, 4. 1, 2, 3, 4. I will just grab a copy.
Yeah, but you can also counsel people. Yeah, we will speak out to them, and then send them. How much? You want to write this mark?
We see the test for the sound system. 1, 2, 3, 4. What? Can you hear us? You cannot hear me? Ah. Yeah, I know. I will just stop sharing the slides and they will put them back. Yes, I think so. Mark, can you speak so that we can test the sound? Yes, we can hear you. Yes, we can hear you. I can hear you at least. Can you say something again just to check if the people in the room can hear you? It's not the best. No, we can put the sound system from the jury members. Yes. Okay, I will share my screen again. Okay. Yes. Hello, Martin. Can you hear us? Hi. Hello, Gavin. Can you hear us? Thank you. Yes. Hello, Peter. Can you hear us? Okay, thank you. We are just setting up the sound system on the room here, and we will start in a few minutes. Okay? Okay. 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 We are still facing some. We are okay. It is an improvisation one. Hello? Hello? It's okay now. Okay. So 6 minutes behind the student. I think we can start now. Just 1 second.
Yeah, so hello everybody. So I'm Federated Learning, researcher at CNRS. So I will be president of the jury. So we are very pleased to have as reviewer of the manuscript of Othmane Ttile, who is professor at the University of Science and Technology. Second reviewer was Mark Mazi, professor at University of Lille. And as a member of the jury, we have Martin Jahi, professor at FedAvg-like, and Gauri Joshi, professor, associate professor in Carnegie Mellon University. And we have an invited member, Laetitia Kamene, who is here in Sofia, which is the lead of AI R&D in Accenture Labs. And of course, we have Jonathan Lega, who was director, who was supervisor of the plan this year. And it's a pleasure to have Othmane here with whom we presented his work. And so Othmane, you have 45 minutes.
I'll start now. Okay, so before starting this talk, I wanted to thank people present here today and thank the jury members and the reviewers for their feedback on my manuscript. And thank you all for all your effort and all of your time. And I will start the presentation now. So this is the presentation of my PhD thesis, which is on pattern heterogeneity in federated learning systems. So this talk will be in 3 parts. In the first one, I will give motivation and will give an overview of the contributions of this thesis. Then I will move to a specific contribution, which is on pattern statistical heterogeneity via personalization. Finally, I will give an overview of the other main contributions of the thesis before concluding. First, start with some motivation and background. So as many of you may already know, machine learning models rely on data that is usually collected by end users while using some applications that relies on those models. The standard approach of training machine learning models, at least before 2016, consisted in moving the data to a centralized location, usually to the cloud, and training the central model there, then sending it back to all the clients. This process has 2 main drawbacks. The first one is that sending data may be too costly from a communication point of view. And the other one is that sending data to a central location can be sensitive and can reveal some private information about users. In order to handle these 2 limitations, McMahon and the co-authors in 2016
proposed a new paradigm for distributed machine learning called federated learning. They later published this paper in 2017. And since then, the term federated learning have seen an increase in occurrence in scientific papers, as we see in the figure in this slide. The federated learning problem has a baseline algorithm that was proposed with this paper, which is called federated average. This algorithm is, in principle, a version of local stochastic gradient descent that aims to solve an empirical optimization problem over the aggregated data of all the clients. The trick used to make this process distributed is by rewriting this global objective function as a weighted sum of local functions, as we can see in this formula. With this trick, the algorithm to learn and to minimize this global objective function can be explained as we see in this slide. So the algorithm is iterative, and at each iteration, a server selects a subset of clients that are active, broadcasts the current copy of the global model, then each of those clients uses this model and runs few iterations of local SGD using their data in order to find a new local model. They send this back to the server, and the server aggregates the results to produce the new model, the new global model. This algorithm has been studied in a few papers and was shown to converge to correct minimizers and their proper assumptions. However, few limitations appear, and most of them are related to heterogeneity. This heterogeneity has three levels or three aspects. The first one is the system heterogeneity, and this one is usually related to the different communication and computation capabilities of the different clients that are participating in the federation. The other one is related to the client's availability, which is usually correlation. So different clients have different availability patterns. Besides the system heterogeneity, we have the statistical heterogeneity that is usually related to the fact that clients collect data with different behaviors. So they have imbalanced data both in number and both in statistical properties. The third source of heterogeneity is what we call temporal heterogeneity. And this one is usually related to the fact that clients keep collecting data through time, and sometimes from varying and non-stationary distributions, which is a phenomenon called conception. Other challenges are related to federated learning besides the heterogeneity, and they consist mainly in privacy, expensive communications, robustness, and lack of benchmarks, besides other challenges. In my thesis, I have mainly focused on heterogeneity, and I have co-authored 5 papers. I have co-authored 5 papers in this direction, for which I am first author, and they are the papers shown in bold here. And co-authored other papers for which I am not first author that are handling other challenges, such as developing benchmarks for federated learning and studying empirical privacy in federated learning. In today's presentation, I will mostly focus on statistical heterogeneity, and I will present my contribution to this to handling this type of heterogeneity via personalized models. My presentation is based on my 2 papers presented in Europe 21 and ICML 2020. Now I will move to the second part of the presentation on handling statistical heterogeneity via personalization. So a first question that one may ask is, why do we need to personalize in the context of federation learning? The idea here is that clients collect data locally when users are using some applications. Therefore, the clients have varying behaviors and preferences. This poses a dual challenge on the learning problem. On the one hand, we have no convergence, which is basically due to client drift. In order to handle this issue of client drift, many papers have been proposed, such as scaffold and proxy scheme, that tries to mitigate the client drift effect. My research was not really focused on this first point, but mostly related to the problem of varying preferences. What we are saying here is that a common model suitable for all clients is not always possible, and it is sometimes suboptimal. So considering, for example, a longest model in application where we need to predict the next word, this next word can vary from one user to the other. So for example, a sentence like I love teaching can have a different next word based on who is the user. Therefore, having one single model to be served to all clients is not really optimal. And this is why personalization is a necessity in many federated learning applications. So I will give now some basic notation that I will use throughout this talk. And in this talk, I will always consider a set of classification or regression tasks which represent the set of all possible clients. This set can be countable and infinite to represent the scenario where a large number of devices is participating. And those devices, we cannot see all of them throughout the training process. But usually, we will focus on the case when the set of clients is finite. And in this case, I will denote exceed the number of clients. Each of those clients have a data set, usually of labeled samples, that are drawn according to some local distribution probability piece. I will use small n to denote the total number of points and small n of c to denote the number of points that client C has access to. Now, each of the clients want to minimize its local population risk, which is given as an expectation with respect to its local probability distribution. And since in general, clients cannot have access to this local probability distribution or this underlying probability distribution, they rely on having access to an empirical risk associated to the clients. So the empirical risk is just the average risk across the points collected by each client. Now, in most of this talk, the hypothesis class is usually parametric with a parameter zeta. So this represents the parameters of a neural network or of a linear model. And additionally, we use DH to denote the pseudo dimension of the hypothesis class. The pseudo dimension is a generalization of the standard VC dimension in the case where the statistical learning problem is not a binary classification problem. Now I will remind two basic generalization results related to federated learning and in general to statistical learning theory. So the first one concerns the purely local model. The purely local model is the one obtained by minimizing the local risk of each of the clients. And back learning theory tells us that the generalization gap of this local model will be upper bounded by a term that depends inversely proportionally on the square root of the number of points that client C has access to. So in general, this number is small in many federated learning applications, therefore the generalization gap will be big. On the other side, the global model, which is the one, for example, obtained by federated aggregation, and that minimizes the risk of the aggregation dataset across all clients, have a smaller generalization gap that depends on the total number of samples, but this comes with the cost of a discrepancy and a bias term that doesn't go to zero. This discrepancy term measures the distance between the average distribution and the distribution of the client of interest. So if one specific client is very different from the average, the bias term will be big. Now, the question that we are trying to answer in this chapter of the thesis is what is the optimal trade-off between those two ends? So what is the optimal trade-off between having a purely local model and having a global model? And how can we achieve this trade-off? This is basically the question that we are trying to answer in this part of the thesis. This question was asked by many other researchers, and the literature on personalized federated learning is quite rich. and it has many methods that I group them in this slide. The first group of methods are the model-agnostic meta-learning-based approaches. This group of methods considers training a global model for all clients that is suitable for personalization and adaptation at each local client. Some researchers have made the parallel between this paradigm and meta-learning, where we train a global model for multiple tasks, then we train this model for few such classification, for example, on each of those new tasks. Another group of personalization methods is clustered federated learning. And as the name indicates, the idea here is to cluster clients into groups, and each group trains separately from the others. So, for example, this includes CFL and IFCL. Later, and in our paper, FedEm, we introduced the idea of soft clustering, even if we didn't really highlight the fact that our method is a soft clustering method, but it can be interpreted as a soft clustering method where the clients do not belong to a specific cluster, but they have a probability of belonging to different clients. Later works have built on our mixture assumption and have highlighted more the aspects of soft clustering of this method. A third group of methods consists in learning shared representations, where the idea is to exploit the capability of neural networks to extract good embeddings and then build local classification or regression models on top of this joint representation. Our Guinean paper is included in this group of methods. Another approach is model interpolation, where the idea is to interpolate a global model with a local model. And again, our Guinean paper is also included in this group. Another approach, which is more or less conceptual, is federated multitask learning via task relationships. The idea in this group of methods is to add a penalization there that captures the structure of the relationship between the clients. The general formulation of this method is quite generic and hard to solve in general, but some simplifications to the structure of the problem can make the problem tractable and easy to solve, as done in L2SGD, for example. Finally, I wanted to mention a new direction of research in terms of personalization, which is framing personalization as a stochastic optimization problem with biased gradients. Usually, those methods lead to gradient filtering algorithms similar to all for all and all for one. Now, I will start by an impossibility result that is telling us that federated learning is impossible with no assumptions on local data distribution. This is in the sense that one cannot improve the sample complexity of the learning problem without having some assumptions on the local data distributions. The proof of this result is by reduction to semi-supervised learning. So first, assume that the marginals over the input space are identical across clients. This is a simplification assumption for the truth. Now, since the conditional distributions of y given x can be arbitrarily different, the problem of collaborative learning with C clients is equivalent to C semi-supervised learning problems. And since with no assumptions on the data distributions, semi-supervised learning does not improve complexity, then the same thing holds for collaborative learning. Motivated by this impossibility result, we have framed two assumptions on the local data distributions that leads to two different algorithms. The first one is the mixture assumption, and the second one is the shared representation assumption. I start first by the mixture assumption. The idea behind this assumption is saying that there exist m underlying distributions that are unknown and denoted on the left of the figure, and the local data distribution of its client is a mixture of these underlying distributions with some mixing coefficients that are also unknown and that are presented here with pi star. So the assumption can be mathematically formulated with the generative model presented in this slide. And it enjoys a good aspect, which is that it's quite generic and it can generalize other existing frameworks for personalized federated learning. And maybe the most clear example is clustered federated learning. So the mixer assumption can recover the clustered federated learning assumption by supposing that the number of underlying distributions is equal to the number of groups, and by forcing the mixing weights to be one-hot encoded. And indeed, this shows really that the FedEm and the mixture assumption are a soft clustering method. Now we can also recover other frameworks for personalization that are not shown in this slide. The question now is, how can one learn under this assumption? And here I show this proposition that is stated informally, and the proposition is saying the following: if one can maximize the likelihood of the generative model shown in the previous slides and obtain maximum likelihood estimators, zeta breve and pi breve for this generative model, the optimal hypothesis for client C can be obtained as a mixture of the hypothesis of m components with maximum likelihood mixing coefficients. So in the figure on the left, we see that for each base distribution, we learn a component denoted with the same color. Then the clients get their local models as a mixture of these base components. So obviously, the clients give different weights to each of the components, as shown on the right side of the figure of this one. So this gives us a straightforward way to learn within a mixture model. So first, we will need to solve or approximately solve the likelihood maximization problem. Then use the previous proposition to obtain the local models for the participation clients. Additionally, clients that do not participate to the training can also get a personalized model by computing their optimal mixing weights through a single forward pass of the models, of the base components. Now the challenging part maybe of this framework is to maximize the likelihood of the generation model. So the natural approach to solve these optimization problems is via the expectation maximization algorithm, which can be decoupled into two steps: an E step and an M step. So the E step is the expectation step, where one updates the belief on the source of on the components from which the examples come from, and the M step updates the parameters pi and zeta based on this belief. So what we can notice from this update rules is that the E step and the first part of the M step can be performed locally without the need to any collaboration, while the second part of the M step requires some collaboration between the clients because of the summation there across the different clients. This reminds us of the initial problem of federated learning, which also consisted of minimizing an objective there, which is a summation over the local data, over the local risks of all the clients. So what we do here is that we use the same idea of federated learning and federated averaging, and we develop a similar algorithm. So in this algorithm, we also have central server and clients. Each of them holds M models and updates them as follows. So in the beginning of the iterations, the central server broadcasts the M copies of the components to all the clients. the client use those local copies to update the parameters pi and the q, then use them to local updates of the parameter theta, and sends back the parameter theta to the server for aggregation. And this process is provably convergent, as we show in this theorem. So under some these assumptions, we prove that this algorithm leads to a stationary point of the optimization problem, both in terms of the parameters theta and pi. So this theorem is telling us that we have a stationary point of the maximum likelihood problem if we run enough iterations. In order to prove this result, we have extended the standard centralized framework of zero-gauge optimization to develop a new framework that we named Federated Zero-gauge optimization. This framework considers the minimization of an objective function that is a weighted sum of functions that depend on two variables. The first one is global and the second one is local. And that each client can compute a first order zero-gauge of the local functions. In addition to its benefit to prove our result, this framework can also be used to analyze the convergence of other federated learning algorithms, including Ttile. Now I move to some experimental results showing the advantages of the federated EM algorithm that we have proposed. So here we are reporting two quantities. The first one is the average accuracy across the clients, and the second one is the bottom decile performance, which is a measure to the fairness of the method. And what we see here is that in most cases, our approach outperforms other competitors from that time, except on the Shakespeare dataset, in which many of the methods behave similarly, and this is mainly due to the small heterogeneity of this dataset. The federated EM algorithm has a parameter M, which is the number of underlying distribution, which is quite important. So we have tried here to study the effects of this parameter, and what we see is that already with two components, we already have an improvement thanks to the personalization, and we see that three components already lead to almost saturated results. Now, a limitation of this algorithm, as some of you may notice it, is that it requires to keep M models and communicate M models, which means that it does M times more computation and M times more communication with the same number of iterations as other algorithms, as federated aberration. And in order to have a fair comparison, we have restricted the number of iterations of FedEm in order to make the total number of communication and computation equivalent to other methods. What we see is that the performance of federated EM we see that federated EM is no longer outbeating all other methods, but it is still doing well on some specific applications, and it is still competitive with others and sometimes outbeating. Before moving to the other method, I wanted to talk a bit on some works extension of the federated EM method. So there were some personalized approaches expanded on the mixer paradigm, and most of them are soft clustering methods. Then there are some other methods that have built on top of the mixture paradigm to develop applications for addressing distributed concept shift and for characterizing internal invasion arrays. Finally, the FedEm's accompanying code provides an open source implementation of many personalized federated learning algorithms, and it was used by other researchers in order to develop their numerical experiments, such as Federico and others. Now I move to the other method, which is personalized federated learning through local memorization. Now I suppose that the set of clients is finite, and I suppose that all the clients have trained a global discriminative model, HS. This can be done, for example, using federated aberration. This HS is similar to what we have seen in the beginning of the presentation, denoted with H bar. I just added the symbol S here to highlight the dependence of this global model on the aggregated data set for the clients. We suppose also that this global model can be used to compute embeddings. So for example, this could be a neural network. The clients build some local data stores using this global model, and the data store keeps the embeddings of the examples alongside with their labs. So every client will build such a quantity. So I illustrate this process here. So suppose that we have a client that has some images and the neural network. The neural network is stored in some intermediate layer, and the client will pass the inputs through the neural network and project them to a latency to provide to compute. This is the computation of the embed, and this is done for all the examples in the data set in order to develop this local data set. So all the clients do the same operation, and since they have different data points, they will end up with different local data sets. Now, at inference time, given a new input, the clients pass a specific client passes the input through the neural network and gets its embedding. The embedding is used to a kind mechanism is used to have a prediction based on the embedding, and at the same time, the global model output is given by HS of X. Finally, the client combines the prediction of the kind mechanism and the global model in order to have the final personalized model. This algorithm have some guarantees under the representation assumption shown here. This assumption is telling us that if two samples have close representations, as they noted with the orange term, then their labels are likely to be the same, as shown in the blue term. But the dependence between the representation distance and the label distance is through a coefficient that depends on the quality of the global model for client C. So if the global model is very suitable for client C, the coefficient is small, which means that the representation influences more the distance between labels, the probability of the labels being the same. We verified this assumption empirically, and we indeed see a linear correlation between the quality of the global model and the quality of KNN, which validates this assumption. So under the representation assumption, we can bound the generalization error of the local memorization mechanism. I provide the result in the case, in the non-agnostic case, in which we suppose that the local model, that there exists a local model that makes the risk equal 0. There is a missing equal 0 here that I have just noticed. So under some proper assumptions, the error of the local memorization mechanism can be bounded by a sum of two terms. The first one is similar to the generalization error of the global model that we have seen in the beginning of the presentation, and the second one is the generalization error of the purely local model. Obviously, when lambda c is equal 0, which means that we ignore the local model, we recover the generalization error of the global model, and otherwise, we recover the generalization error of local KNN, of the local KNN algorithm. So again, we do similar experimental results as before, and we notice that KNN pair is also outperforming many of the competitor methods. The KNN pair algorithm enjoys another ability besides besides the possibility to tackle statistical heterogeneity. So this algorithm can, for example, be used to handle system heterogeneity by allowing clients to adapt the size of their data store with respect to their memory capacities, for example. So in this slide, we have done two tests varying two quantities. The first one is the capacity, which shows how much the performance improves by adding more samples, and the other aspect is by changing the level of heterogeneity. Smaller values of alpha means more heterogeneity. What we see is that the method have more improvements when the heterogeneity is higher and when the number of samples increases. Another aspect related to the ability of Kine pair to handle system heterogeneity is the possibility to add in compression techniques on top of Kine pair. So the compression is done on the local data store. So for example, stronger clients can use the true local data store, while weak clients in terms of memory capacities can use strong compression techniques. But in all cases, what we observe here is that we can obtain 4 times savings in terms of memory without a significant loss of performance. Another nice property of the memorization technique is that it can also handle distributions. So we suppose that we have a case of a data stream where the underlying distribution changes over time. And we simulate such a process where we have a change in the term of distribution in the middle of the train. The local memorization technique can adapt to this shift with time and can find the new optimal mode. So here we have developed 2 local cache methods to update the local data store, but we don't provide theoretical warranty. So before moving to the other contributions of this thesis, I will stop with a comparison between FedEm and Kine. So on one side, FedEm and the mixture assumptions are flexible and generic and can also be used to quantify data distribution similarities among clients via the distance between the mixing coefficients. But it has a problem that we have seen due to its local communication and computation overhead. On the other hand, Kine pair is a simple and lightweight model that can be added to standard federated learning algorithms, and this can also be used to handle statistical system and temporal heterogeneity. However, it's not very suitable as a modeling tool, and it cannot recover all the other frameworks of personalization as federated EM. So now I move to a summary of the other contributions of the thesis, besides statistical heterogeneity. So the first part is on system heterogeneity. And this is due to the fact that clients have variations in hardware specifications, in network connectivity, and in power availability. And this shows in 3 distinct scenarios. The first one is the cross-silo settings, in which entities that are having good computation and network capabilities are trying to collaborate with each other. In this scenario, the different data silos have varying pairwise communication capabilities. And in this case, having an orchestrator-centered topology is maybe inefficient. And in this case, peer-to-peer communications can be better. In our NERIPS 20 paper, we studied the question on how to design communication setup that allows for faster conversion. The second scenario for system heterogeneity is in the cross-device setting. And in this case, the different mobile users have different availability patterns because of the system constraints on the battery, for example. Usually, the availability patterns are heterogeneous across clients and correlated. So some clients are very available, some others are less available, and some of them have correlated availability pattern. For example, one client can be available all the night, then not available during the day. Many works study the problem of client availability, but most of them rely on simplistic assumptions such as independent availability patterns, and they usually ignore correlation. In our paper from 2023, we studied this problem under Markovian client availability. The third aspect of heterogeneity is in the case where we have of the system heterogeneity is in the case where we have different hardware from the different clients. So some clients have strong capabilities while other clients are weak. For example, some of them are entities while others are mobile users. And in this case, it is suboptimal to restrict all the clients to use the same architecture. And an important question to answer here is how to relieve the most powerful clients from the need to align their model to the weakest one. And as shown before, our kind pair method partially answers this question by relieving the strongest clients from the necessity to aligning with the weakest ones. Now, the other source of heterogeneity is the temporal heterogeneity. And the idea here is to learn in collaboration, but also in dynamic environments. This question of learning in dynamic environments is relatively unexplored in the context of federated learning. So first, learning on statistical datasets is usually suboptimal and is sometimes impossible. It is suboptimal because it ignores the new samples collected by the clients, and it is sometimes impossible because some clients are too constrained in terms of memory and cannot hold any of the samples in their local memory. Besides these issues, we have the distributed concept drift, which is caused by client having varying underlying distributions across time. So we have two contributions in this regard, and we have two learning algorithms for data streams in two scenarios. The first one is the stationary regime, where the underlying distribution don't change across time, and the second one is the scenario where the data distributions, the underlying data distributions, are changing based on a restricted adversarial model. Besides these contributions related to heterogeneity, we have two other additional contributions. The first one is regarding privacy, and this is an empirical, it is a study of the role of reference data in empirical privacy difference mechanisms. The second one consists in developing a benchmark for a benchmark and the dataset for cross-silo federated learning in healthcare applications. So before ending the presentation, I wanted to stop with some of the possible future research directions that I am grouping in this slide. So one first research direction is the quantification of statistical heterogeneity. Some of you may have noticed it during the slide, the presence of this discrepancy there that will impact the choice of the hyperparameters of FedAvg and KNM, and especially the aggregation parameter of KNM. The discrepancy there is usually unknown and should be estimated from the data. And this is a still open question. Our FedAvg algorithm, for example, presents a partial answer to this question, and it's because its mixing coefficients can be a measure of statistical heterogeneity. Another aspect now related both to system and statistical heterogeneity is the design of topologies or communication setups that are aware on the data heterogeneity. There are already some works in this direction, but this is still an open question. A third line of research related is related to privacy preserving personalized methods. So for example, the clustering method is not very private because it reveals the group identity of the clients. So for example, the soft clustering method proposed by our mixer assumption can tackle this issue and mitigate it because the clients now do not belong to a specific cluster or group. Instead, they only partially belong to one of them. So this information can be hidden by adding some noise to their coefficients or to the upgrades that they need to be set. And this is also an open question, even if some recent works have tried to handle privacy preserving personalized acceleration. The third rule is developing local cache update rules for federated learning, and this is in particular important for kind pair when used to handle temporal heterogeneity. So for example, we have studied two update rules in the experiments where we have seen how kind pair can handle temporal heterogeneity, but theoretical studies on the warranties can be also a good research direction. Finally, an important research direction that is gaining attention lately concerns incentivizing client participation in federated learning. So the question here is, how can I incentivize clients to participate in federated learning, even if I usually don't give them guarantees that they will have benefits by collaboration? So this is also a question that is analyzed by many researchers with game theoretical frameworks, for example. So with this, I come to an end of my talk. Thank you all for your attention, and please let me know if you have any questions.
So, thank you, Othmane. We're on time, perfect. Okay, so we'll start the session of questions. So the tradition is to start with the reviewers and select between the reviewer to start with the farthest away one. So it will be Peter H. So we'll start the question. So Peter, you have the floor. Can you hear us well? Yes.
Peter, can you hear us?
All right, so very nice presentation. So I have some questions, but I will ask all of them. So one question that I have is a bit more of a philosophical one about the F.D. So I understand the setup, the reasoning behind it, so the idea that something like that should have been done maybe many years ago. So I believe it's a very interesting contribution to the literature. However, the question that I have is that structurally, when you compare the algorithm and the implementation steps, structurally, the algorithm will look differently from methods such as aggregation, even though, of course, there will be some local order and some individual stuff. And you should try to think of reverse engineering maybe the right problem, not right formulation from a right formulation for which maybe aggregation would actually be something like Federated. I'm trying to think in this direction. Does this question make sense to you?
Okay, I will try just to rephrase your question to make sure that you understand. So what you are proposing here is how can one check the federated averaging algorithm and modify it in order to obtain the fit here? Is my understanding correct?
Right. So maybe one would run something like that in everything. You do the same thing, but maybe for different functions in order to obtain something similar to that. Now I know this is very big, so maybe even your interpretation is fine. This is what I do.
I think I have a better understanding now. Can you still hear me? I just switched mics. Can you still hear me? Can you still hear me? I have just switched mics. Maybe not. Okay, I will go back to the original. No. 1 second. Okay, can you hear me now? Okay. Okay. So what you are proposing, if I understand correctly, is to have federated averaging algorithm, but consider a different objective function, for example. So let's say a different objective function for each of the clients. Is this a correct interpretation of your question? Okay. The idea here would be to have a local objective function that have the same behavior as the updated one from FedAvg. So the idea, I can make a parallel between what you asked and the FedAvg algorithm. In the FedAvg algorithm, we are using federated averaging with some local functions, but those local functions are varying across time, for example. So this part of the summation can be seen as a local objective function, but this local objective function is updated at each iteration.
However, those local functions are not exactly those that we consider. Is there maybe some follow-up question? Is there maybe some understanding?
Yes. Yes. So a good example of methods that also are using federated averaging with a local function that varies across time are, for example, federated procs, in which there is a penalization term that depends on the global model and that varies across time. Another one is the FedU framework, in which we have also a penalization term. We have a local objective function with a penalization term that depends on the global model, which is also varying across time. So those are examples of methods where the local functions are varying across time because the global model is changing. But the way the local functions change in our FedAvg algorithm is particular, is different because it relies on this expectation maximization step, or at least on partial expectation maximization step, while the other methods have a more straightforward computation of how to update the local functions.
So one question is that I was surprised that the interest in very small. I would not expect that. So is there some reason why you don't have so small? Did you maybe generate data in such a way that you can work with you? I would assume that in a realistic setting, and definitely be small compared to the totality of
Okay, so in this particular experiment, we have generated, if I remember correctly, the number, we have generated a data distribution that verifies the assumption with a larger number of components than the one shown in the slide. So we have generated a mixture with 7 components, for example. I don't remember the exact number, but I believe it was bigger than all the values shown. If I remember correctly, which was bigger than all the values shown on the figure. So it's either 7 or 10. But I don't remember the exact value. However, one important thing to consider here is that when we increase the parameter of the algorithm, the hypothesis class gets bigger. So the generalization gap is expected to be worse when we use more components. And therefore, the gain we have by having a more flexible assumption, more flexible hypothesis class is paid in terms of generalization capabilities. So maybe one of the models with large value of m has better empirical capabilities, but it will have worse generalization capabilities. Another aspect is that what happens then in many cases is that the models get entangled with each other. The base components, models get entangled with each other, which prevents them from exploring all the possible directions. Again, our method is only proven to converge to a stationary point and not to a maximizer of the likelihood, which can justify this behavior.
I'm not sure we can.
So the question, so the assumption that we make is that we have n capital N
Okay. Let me just rephrase your question. Thank you again for this question. So what you are asking is whether I can impose a sparsity assumption on the weights by while allowing m to be bigger. I'm sorry?
What would be the problem if you expect this kind of
Okay. I think that, okay, first we will need to update the. Okay, so here we are having a let's suppose we have a layer one penalization in terms of pi. The question here would be how to do the E and M steps. And maybe what will happen is that we will, at each iteration, only keep the, let's say, larger values of coefficients for each client. But what may happen here is that each client will learn alone without collaboration with others. So if we allow a setting where M is very large, larger than the number of clients, what will happen is that each client will have a component that is specific to him. So we will have components that are basically local models. And in reality, this will maximize the likelihood, especially in the non-agnostic case, where the empirical risk for each client will be zero.
So I didn't have in mind formulas. What I have in mind is a formulation where n is specifying vector, let's say larger than something others not good. And one would still assume that the weights, a mixture of all of these, but the mixture is sparse. But the sparsity means that maybe at most lowercase n rather than capital M of weights are actually. Most of them are maybe exactly. The second part is actually so that we avoid the situation where maybe those weights generate
Okay. I believe that this is possible. The issue I can see with this, I will just, okay. So the so what I am afraid about this method is that the client could degenerate and start learning local models. Now we are restricting the number of components to be smaller than the total number of clients. But at the same time, we are having a sparsity constraint. Okay, let's consider the following scenario. Okay, so I will suppose that we have M prime and big M. So big M is the total number of components. M prime is the norm zero of pi that we call it. Okay. So what could happen here is that we will have different groups in which some clients could be on the same cluster as another one. So we will have some sort of okay, this can be modeled through a graph or a hypergraph over the clients, in which clients in the same hypergraph are training the same model. So one client can, so we have four, let's suppose that we have 4 clients. The first one and the second one can be on the same hypergraph, hyperedge. The third one and the second one can also be on the same hyperedge, and the fourth and the third can be on the same hyperedge. Here, the first client and the third one are not belonging to the same hyperedge, but they are still benefiting from collaboration through the second one. So in reality, I think that this idea can be interpreted as a hypergraph clustering method, which I believe there exists one paper that is going in the same direction. And I think that there is a parallel between having 50M with large M and sparsification conditions and this hypergraph structure of the relationship between clients. I'm not sure if it makes sense for you, my answer. Mm-hmm.
So it's the same thing, except the expression knowledge.
Okay. Thank you very much.
Thank you, Peter. So now we are going to the second reviewer, so Mark Evasi. So Mark, can start your question.
Yeah. Okay. So first of all, can we repeat this? I want to say you need the microphone because like
Okay.
And I want first to do education. Very clear the next week. The faculty of because the local street so
I just moved it to the speaker because I want to do you can post it. I'm sorry, Mark, you had a okay, I will move to my mask. Can you still hear me? Okay, we had a loss of connection in the room. I am sorry. I hope that we are back. Yes, I can hear you. I'm sorry, I didn't hear your question. I heard until the part where you mentioned that you have a question about the first part of the manuscript, but I didn't hear the actual question.
Yeah, I was saying, but I wanted to know if the model you have used, it is able to take into account kind of executive access to the data, or something that we consider because we have small clients that
Mhm. Okay. Mhm. Okay. Okay. Thank you for the question. It's a good question indeed. I just wanted to remind a bit of the modelization done in the topology design paper. So we have an underlay and we have an overlay of the network. So in the overlay of the network, we are basically modeling, let's say, internet connections. So the clients have a net or a connection to some routers, then the routers have some communications among each other. And what you said is correct. Some clients can communicate through the same link because they can pass through the same router, for example, or that their routers are communicating through similar paths. So there exists the possibility of sharing links in the network. And this is in fact captured in our delay model where the bandwidth is divided by the numbers of clients using the same link. Now, as a simplification assumption, we have some sort of constant usage of the links independently on the number of clients using them. And this is basically meaning that on internet, even if the clients are participating in our training because they are few, cannot disturb that much the bandwidth of a specific link on the internet, for example.
It's not that it's possible that I have to put this it's what happens if you have now as domestic networks first go I will go to
Okay. Again, thank you for the question. It's quite interesting. Now, in this, I wanted to remind something is that in this paper we have used the theory of synchronization in the max plus algebra, and we basically relied on results from the book of Pacelli on synchronization theory. This book has a specific chapter on stochastic queuing methods on the network and how synchronization can be done in the stochastic case. We haven't really explored this part, and we have mostly focused on the deterministic synchronization. And I wanted to point out that the problem, even in the deterministic case, is already empty hard, which means that it definitely will be empty hard even if you allow for random communications, because the deterministic case is a specific case of stochasticity. So because of this empty hardness of the original problem, we didn't really explore the stochastic modelization, which is even more challenging. However, I think that so we have relied on this quantity, which is the cycle time. Basically, that's what we have got from the synchronization theory. And I believe that even if you have a stochastic model for the network, you will still end up with an equivalent quantity to the cycle time which will also be computed in a similar way. So the problems are in reality similar in some sense, because in both cases we will want to minimize we will want to minimize some quantity that is similar to the cycle time. It's just that the formulation of the cycle time can be a little bit different from the one we have in the paper. But it won't be fundamentally different thing. Is my answer meaningful for you?
Last question because when we covered that the team of was kind of what was the great gaps. And so is it the same conclusion you have some figure of
Okay. Okay, thank you again for the question. There are 2 points that I wanted to mention. The first one is that the optimal topology will depend on the specific modelization of the system. So it will depend on the values of the bandwidth, on the upload capacities and download capacities that you have on your system. In our paper, we have used some realistic values for these quantities that we have obtained from real topologies in the world. The second point is that we do not really say that the ring is the optimal topology. What we are saying is that we have some guarantees that the ring topology, if the ring is ordered in a correct way, can approximate the correct solution with some given approximation factor. And we are saying that among the topologies that we have compared with, the ring is doing better. So it is possible that some other topologies are still having a better performance than the ring. An additional point that I wanted to add is that the ring topology is normally the best in terms of cycle time. So the fastest iterations possible you can do are the ones with the ring, because each client will only communicate with one other client. But the problem with the ring topology is that we will need a lot more iterations. And the number of iterations that we will need to do will depend on the heterogeneity of the statistical datasets. So what we have done in our work is that we have some sort of realistic partition of the data of the data across the nodes that is appearing to be not very heterogeneous in my opinion, because we have partitioned some naturalist data set across clients geographically. And in fact, this is an image data set. So the underlying distribution does not change much, because an image of a dog will be still a dog, whether you are in the US or you are in Europe. Dogs are mostly similar in many countries. Now, some other species may change, but I think that the main reason why we have strong performance for the ring in our scenario is the fact that the heterogeneity is not that strong.
What is your
Okay. I 1 second. I will just get the thesis in front of me because I don't remember the exact. One minute. I will share the manuscripts in the screen. Mark, can you please repeat what are the assumptions you have mentioned and the page, please? Okay. Yes. Okay, I understand the question. Okay. Okay, but okay. I understand the question. Okay. Thank you for the question. So you are no, it's not yes. Yes, yes. I will just share my screen because I didn't do it. Okay. I will stop sharing and I will share again. Okay. You can see the manuscript right now.
Yes.
Okay. So you are referring to the separation assumptions in the EM for the EM algorithm in the Gaussian. Okay. Those assumptions are, as you said, necessary for the for the uh, for the training, and they are normally necessary to prove that one can recover the Gaussian mixture model. Uh, I have provided a remark 7, saying that those assumptions can be replaced with middle ones at the cost of running one step of Cummings. So what we are saying here is that by running one step of Cummings at each iteration, and if you suppose that the data is separated, that the Gaussians are separated, we will get the initialization assumptions that we want. But this comes at the cost of running one step of Cummings. No, in reality here you have mu star and the mu j star, not your guess of where the means are. So there are two things. There is the mu 1j, which is the your estimate of where the mean is, and there is mu j and the mu j prime that are the correct places for where the means are. Now, the positions of the means, the real positions of the means, you don't control them. And I agree with you. We supposed in the beginning that we are handling well separated Gaussians. If the Gaussians are not well separated, you cannot hope to recover them. So here we are supposing that the Gaussians are well separated. This is something I don't say that we can get rid of. What I am saying that we can get rid of is that we do not need some oracle to give us a good estimation of the positions of the means. Assumption 28 is basically telling us that you need a good estimation of the means. So suppose that you have an oracle that gives you mu1z. Now what I am saying is that K-means is an oracle that verifies this. That's what I am saying. See, in assumption 28, I was telling that you have an oracle that gives you mu1. And in the remark 7, I am saying that K-means is a good oracle. Does it make sense? If not, I can rephrase my answer.
what to do
Okay, thank you again for your question. It makes sense for me. There are two things that I wanted to say. The first one is that what you said is correct. Yes, this kind of analysis can also be used to analyze privacy preserving OMD, for example, because private OMD will also have a noise. Will also use some wrong gradients, let's say delta H, that are far from the correct one with a noise epsilon. And definitely we will get some result here in expectation of this noise, which will be probably epsilon square, which is the variance of this noise. But I wanted to mention an important thing is that this result is not that challenging, in fact, and it's a straightforward computation. So definitely it can be used to analyze privacy preserving OMD, but I think that this part of the analysis leading to theorem 4.4.3 is not that challenging. And maybe it was a mistake to call it theorem, it should be more called it lemma 4.4.3. But yes, what you said in the beginning is correct. This is a result that can be also used to analyze private OMD.
And want to know which managed you have kind of communication or ability that you know
I'm sorry, I didn't hear you.
if you have a method
Okay.
that you know communication or the application the methods that proposed to that really that is working when you check this job. Do you think that provide some kind of test that really
Okay, thank you again for your question. Let me just rephrase to make sure that you understand. So what you are asking is that for all the methods we have developed, maybe which ones consider communication explicitly, and which ones considers developing are developing strategies that are optimal in terms of communication and computation uses. Is this a correct interpretation of your question?
can be if you take consideration the example of the energy consumption, you will have a container for let's say normal conditions, like that. So if I want to maximize the results, maybe just counting instead of the region at each time instead of the question to can add I don't know if it's possible to analyze that
Okay.
because maybe it's not the best thing to do to start. I want to get to that possible strategies. It's a kind of analysis.
Okay. So just for me to be sure, you are now referring to the OMD part of the thesis, right? Or you are referring to the thesis in general?
In general, I think maybe can be more
Okay. So let me just now try to re-understand the question. What you are saying is that I have a strict budget given in the beginning of the training in terms of communication and computation. That's this is the framework you are considering, right?
Yes.
Okay. And now the question you are asking is, how can I use this budget optimally? Is this correct? Hello? You do anything? Hello? Does it? Yes, I'm sorry. We are facing some limited bandwidth problems in the room. I got disconnected by the system. Okay. Let me just go back to what you were saying. So I was trying to understand the question on the communication and computation budget. So we agreed that we are in a setting where the communication and computation budget is given from the beginning. And my question now is, do you want? So your question is about developing algorithms that are optimal with respect to this budget. So having optimal performance for a specific budget. Is that your question? Okay. So this is quite a challenging problem, in fact, because most methods will have a trade-off between these quantities. So I will a good example in my thesis that reflects this question is the communication design question. So in this problem, we are trying to design a communication topology, or I will repeat it in this way. So in this part, we are saying that having a distributed or a fully decentralized optimization framework will have two effects on the communication and computation budget. So on one hand, if we have sparse networks, each iteration will cost less, but we will have more iterations. But on the other hand, having a dense network will lead to slower iterations, but we will need few of them. And then in reality, what you are asking is to design a topology that matches this problem that I will show now. I'm not sure if I have a formulation for this here, but what we will want to do is to maximize or minimize a term that has the cycle time and the eigengap of the network. Now I want to note that optimizing the first part is already empty hard, which means that optimizing this aggregated term is also empty hard in general. And therefore, it's quite challenging to find a topology that is optimal in terms of both quantities. But your question definitely makes sense because, for example, one can consider a specific level of accuracy that one wants to achieve, and then will draw some convergence bounds that and replace the total number of iterations by the total amount of computation needed, by multiplying the total number of iterations by the delay required for one specific iteration. So the idea will be like fixing an error epsilon. For this error epsilon, the convergence bounds tell us how many iterations we need to achieve this error, and then we multiply the number of iterations by the duration needed to perform one single iteration, then optimize this quantity. Again, what I am saying is that this problem is in general NP hard, and I don't think that it is easy to solve optimally, but it is possible to develop algorithms that go into this direction. And our first paper on topology design is trying to solve this problem by saying that the effect of the graph on the eigengap is dominated by its effect on the cycle chunk.
Okay, thanks a lot, Mark. So now we go to the member of the jury, and the first one is Gary Rochi, who is associate professor in Carnegie Mellon University. So Gary, you have the floor. What's your questions?
Sure. By the way, I cannot hear you.
You cannot hear me or me?
I mean, is it better now?
I think so. First of all, I want to give you an explanation. So, you already answered some of the questions about cost of one thing I wanted to ask is, when you talk about privacy, because you're sharing extreme rates between the cycling server and the clients, and extra rates can give you information about things. And this is a common problem that occurs with trusted rates versus.
Yes. Thank you very much for your question. And I maybe have quickly mentioned this while presenting the future research directions. And as you mentioned, clustering algorithms are not really private because they reveal the identity group of each client. Now, what I am saying is that such clustering algorithms relatively mitigate this problem because now clients no longer belong to a specific cluster, but they have a probability of belonging to each cluster. So one can add some noise on this probability in order to protect the privacy of the client. So we didn't do this analysis ourselves, but we have mentioned this possibility in the conclusion of the chapter of FedEm, that one can add some noise and mitigate the effect or the privacy issues of clustering using soft clustering techniques. But we didn't do the analysis ourselves.
Okay. Another question related to third reactions. Have you thought about how to modify the maximum life concepts? You mentioned like maximum centers and
Okay. Yes, that's also a good question. To be fair, I am not very familiar with all the literature on incentivizing federated learning. I just started exploring this in the last couple of months. But my belief is that the federated EM algorithm itself shares a lot of similarities with federated averaging. Because in reality, and as I mentioned during my answer to Peter, we are trying to solve a distribution optimization problem where the local objectives keep changing. And my belief is that whatever technique can be used to incentivize clients to participate in the standard federated averaging scenario can also be used in the FedEm algorithm from a conceptual point of view. However, I cannot give a precise answer, as I said, because of my limited knowledge about this direction of research.
And I think my other two questions are more clarification questions on some topics that we mentioned in the presentation. So first is about the distribution. I don't fully understand how the
Okay. So this part is quite empirical in fact. So the idea of the algorithm is the following. You have a global model that is fixed all the time. And this global model has a local data store, okay? So the local data store could get updated when receiving new clients. So when you receive when receiving new samples. So once you receive a new sample, you embed it into your data store and you add it to your data store. So what happens here is that when you receive the new points, your local data store gets updated to the new distribution. So for example, in this scenario, we have a first distribution, then a second distribution. So the local data, now I will precise the case of FIFO kind of update rules for the local memory. So what will happen here after the distribution shift is that the new samples will replace the old ones in the data store. And therefore, the points that exist in the local data store are from the new distribution. After enough time, all the local data store will be built using the new data distribution. And therefore, the prediction of the local normalization technique will be adapted to the new underlying distribution. Does it make sense for you?
Yes, but you don't know when the distribution switches, right? Or you don't know that time. So.
Yeah. So thank you for this question. In reality, here the method is agnostic to the distribution shift. See, the local data store is updated when you receive a new client. Now suppose that you have a data store that you update it with a FIFO rule whenever you receive a new sample. Now independently, you don't know if this new sample comes from a different distribution or not. But when it comes, it just ejects an old sample that was in your memory. And just by using this strategy, let's say that you have this particular scenario here, the local data store will update automatically when you have the distribution shift because it will start having more points from the new distribution.
Oh, I see, I see. So it's not forgetting the old distribution points.
Yes, it's just a FIFO rule where the old samples get removed before the new ones. So the strategy should... Yes, and as I wanted just to clarify this is a purely empirical and the side effect of the method, and the method was not designed for this, and we don't have any formal guarantees for it. It's just a remark or a side effect of the method, as I said. It's not like its main purpose.
Thank you. And my last question is about the
Yes. Yes. First, I wanted to apologize for the mistake that happened. That I think that I have done a mistake on LaTeX. We didn't show the publication. I'm so sorry for this. So the idea in this work is that now the clients have a Markovian availability process. So the process of availability of each client is Markovian. We do a general analysis where the states of the Markovian process are the availability of all the clients, and we have a transition matrix for what is the next that matches the probability of the next possible clients if we are in a given state. So this was done for the general analysis, but we have also in the experiments and in the algorithm side focuses on a specific case where we have steep parallel Markov chains. So each client is modeled with a Markov chain of two states, active and inactive. And then the clients, so a client that is active now can get more active in the next round or not, based on this transition matrix. And the algorithm that we have developed, or the theoretical results that we have developed, shows that if the Markov chain is more correlated, the convergence will be slower. Or in another sense, clients that are more correlated or having a more correlated activation patterns will slow down the convergence because they get active more than the others. So our algorithm tries to detect declines that are more correlated and somehow remove them from the training, at least in the beginning, and at the same time try to compensate for the different availability probability of declines. That's basically what the algorithm is trying to do.
Okay, okay. I think that's all of my questions. Thanks again.
Thank you very much.
Okay, thank you. So we go to the next member of the jury, so Martin David, professor at the TFM. So Martin.
So, I mean, we started that saying that there's no possibility to discuss that with definition assumptions, but then at the end, that's very, very deep assumptions and so the question is if you want to quantify this, is there what other type of quantities that you might want to use for that measuring the efficiency of distributions, the information, and then also the single insights, how insights
Okay. Thank you for the question. I will just try to rephrase to make sure that I understand because I am not sure. So what you are saying is that we have an impossibility results that is saying that we need some assumptions to learn. Then what you are saying is that our FedAvg algorithm does not impose strong assumptions on the distributions. That was the first part of your question. Is this correct?
Yes.
Yes.
For example, when it's one client, just one species, more than one client, it's one altogether, one client, that's distribution, and another assumption is distribution.
Yes. Okay, I understand your question. So the answer to your question is that I expect, even if we didn't prove that the generalization. So I wanted. Okay, I will repeat myself. So I wanted first to say that we didn't provide generalization results for the EM algorithm. We only proved the convergence of FedAvg in terms of finding the maximum empirical maximum likelihood estimations. So in the paper and in the manuscript, we didn't provide any generalization results. That's the first thing. The second thing is that I expect the generalization gap of FedAvg to deteriorate with the parameter m. In reality, I expect it to be linear in terms of m. And I will explain my reasoning why I think it's linear. This is basically because the FedAvg algorithm can be seen or thought as a boosting algorithm, where we are ensembling multiple models. And for boosting, we have the generalization error that is linearly growing with time or with number of models that we are having in the ensemble. So I expect that the generalization error of FedAvg will be something like n multiplied by the BC dimension of H, let's say. And therefore, if you allow m to be quite large, and let's say equal to c, then in reality, the generalization error will be so bad, and we are still not improving the sample complexity. So the generalization error will be small when we restrict m to be smaller. But at the same time, if we are agnostic, this can include an additive term, which is the performance of the optimal mixture model. But if you are in the non-agnostic case, if you are in the non-agnostic case, when you suppose that there exists a mixture model that fits well the data, then this term will disappear and you will gain benefit because the generalization error is smaller with smaller. So you have benefit when n is small and the data fits this generative model. I'm not sure if my answer is makes sense for you.
Yeah, that makes sense for the decision. I was also curious if it's not the next compensation, like how much faster.
Thank you very much. That's also a nice question. And in reality, in the paper or in the proof, we have made this generic assumption that the local distribution, the local functions should not be very different in terms of the gradients. So we had a standard bounded dissimilarity assumption that did not take into account the local data distributions. But what I believe is that the coefficients in this assumption can be obtained as a function of the parameters of the generative model. So what we did in the proof is that we say the empirical local functions are having bounded dissimilarity with some coefficient b. That's the assumption we started with. What I am saying now is that this coefficient b can also be found as a function of the mixing weights, as you said. But we still didn't do this analysis. I believe it's not quite challenging because it's a rewriting of the generative model and some. I think that some simple algebraic operations can lead to a result similar to this one. But it's a nice question.
Okay, so it's perfect sense. Yeah, just maybe one more question. Also, I was wondering here, and also question is process.
Okay, let's think about this a bit. My first guess is that it won't be because the true technique relies somehow on rewriting. So I will just re-explain the technique that we have used, and I will explain why I don't think that it can capture the asynchronous scenario. So the technique that we have used is basically decomposing the error into two terms. The first term is the distance of the is how far the Markovian chain from its stationary probability. So how far is the Markovian process from its stationary probability? Then we had another term, which is the standard, which is how far would the stationary Markovian process would be with respect to the optimal solution. Then we have used standard techniques for the second term, and we have used results from Markovian process analysis to bound the first term. And I think that the part related to optimization itself is a standard and similar to synchronous SGD. So I don't really think that it can, the technique can be used to analyze asynchronous SGD. Instead, I think that if we allow for asynchronicity, we can have such a model. Now, having that said, it is I think it is maybe possible to recover an asynchronous SGD via some different modelization of the problem. So we can think of it. So we can think of the Markovian process or the availability of the clients so we can have some probabilistic availability of the client that is modeled via Markovian process, and then when clients participate, they use the current gradient and so on. However, I am not sure that this will work fine because in our analysis, all the clients participating at a given moment use the same local model. But for asynchronous SGD, some clients will use a stale model, and I am not exactly sure how our analysis can recover this. So I am not very sure about. I cannot give us a final answer to your question, and I'm sorry for this.
Okay, thank you, Martin. So now we go to the member of the jury which are presenting so far. Maybe Laetitia.
Yes. Sure. I will start with the comments. So you can read first. So first, yeah, thank you, Othmane, for this great presentation. I think really illustrate the density and how deep the research has been during the years. So we have been really pleased actually to collaborate with you and your data, doing your thesis, and then try to set some directions also related to what we see on the business side. So we are very also appreciate different instructions that we have developed for our engineers that will be really important for us to help demystify and also understand the various challenges that we tackle with the development in the field. So yeah, I'm quite aware of all these topics, of course, because we have people to discuss them already. But then maybe if we want to look a bit some more on the business side of things, I'm wondering if you what would be your which concrete, I would say, concrete application use cases, even industry, you see potential impact of your research or any the direct extension of the what you did. They happen in the coming years probably. And this
Okay. Just to make sure I understand the question, so your question is on the possible applications of federated learning in the industrial settings, and what are the major applications for both my contributions and for federated learning in general.
Yeah, and then or if you see any new scenarios or possibilities that could be blocked somehow by this work.
Mm-hmm. Okay, so I wanted first to mention that I believe that in practice, federated learning has still not that is not always applied in all the settings. This is very hard to apply it in practice because of a lot of system problems that are not covered in this thesis. Now there are two applications that are quite possible, let's say. The first one is the medical application, where hospitals collaborate with each other, which I believe is a possible application of federated learning that some other researchers also from India are working on FedBiomed project, for example. And this scenario is quite practical because it's a scenario where collaboration makes sense and it's across silo setting, so the system properties are so the system is well understood and well controlled. The other maybe big application, I believe, is for giant tech companies that have access to lots of resources and have strong privacy constraints. And in that case, mobile applications, this application is mainly concerned on mobile applications. And I think that personalization is an important aspect there. And in fact, I think that, for example, the time-and-pair algorithm could be well used in practice thanks to its low computation and communication requirements. So I think that this is something that could really be applied in practice for this kind of scenario. But still, verifying if those things work or not is still a question. Another thing related to cross-silo setting is this topology design mechanism that we have mentioned it in our papers and that someone tried to work on to propose some framework that can do optimal allocation of AWS or cloud provider services in order to find some sort of nice behaviors. But we didn't push this project that much at the end because of the many things going on during the PhD.
Okay, thank you very much.
Thank you.
Thank you, Laetitia. So before going to Giovanni, Maybe we can do the second other question for a member of the jury that has another question to ask. So I think, Peter, you had other question in mind? You have the-
So let me start with my question that I had about the ask. So one question I wish to ask is about the assumptions. 4, 7, 8, 6, on page 26.
Can you repeat the page, please?
Page 26.
Yes, I am getting it. So
I think I want to focus on something. 4, and analysis plus the assumption of the hypothesis plus the conversation time. Okay, the analysis plus about why they make the assumption. How does it
Yes, thank you for your question. So this assumption for, in fact, is quite restrictive because we are supposing that the domain is bounded. Now, once we make assumption 5 and assumption 6, and especially when we are making assumption 5, this leads to bounded gradients and bounded dissimilarities, which could be, in fact, a bit fake assumption because in our case, now everything is bounded. So if the gradients are already bounded, I can bound the similarity also, and I can bound all the quantities in simple ways. And there are some works that are criticizing, and I believe some of them are from you, criticizing this kind of assumption where we use bounded gradients, and they are showing that this does not enable one to get the optimal convergence results. And here I am referring to the paper with Ahmed Khalid from 2019, I believe, and published in iStats 20. And I think that in this analysis we have a bit followed the easiest path to find the convergence result, and we didn't try to work with the minimal assumption, which is a limitation of the analysis that I recognize.
Okay. So that's it. I think the rest of the questions. Thank you very much. Very nice presentation. Very good.
Thank you. Thank you, Peter. Is there another member of the jury that wants to ask a question? Okay. So, if you think about the question, please have time before, after Giovanni and myself. So, Giovanni, maybe as a supervisor of the plan, you mark our question.
No, I don't have a technical question. It's for me the opportunity to congratulate for all your work. And we've been 4 nights here with a lot of fun, both intellectually and out of many different things. In the office, we're talking about science, and at FedAvg-like, we're talking about everything else. So, yeah, it was just to thank them and congratulate you for the work.
Thank you very much.
Okay, thank you, Giovanni. So, I will not be very long. So I want to congratulate you also for very nice work. You did a very nice manuscript also, which was really a pleasure to read. Very nice presentation, really safe. And you had also some effort to make your work available as open source. It's a very valuable effort. And you even discuss of one of your work that I was a bit curious on the Ttile dataset. So can you tell us a bit that one?
Yes.
So,
Yes. So Flamby is a data set that we have developed in collaboration with many other researchers, including Martin, who is present here today. And it was an effort led by a French-American medical company named Othmane that is proposing some services that are using Federated Learning for medical data. And so this is an effort that was done with a lot of other collaborators. I have personally participated in the coding and developed parts of this benchmark and developed some of its algorithms alongside with other contributors. So the dataset itself is driven by people who are developing real-world applications on medical data, and it reflects as much as possible real scenarios and provides codes that can evaluate and generate, evaluate models on this data, train it from this data, and generate different splits for those medical data. So this was a work that was in early 2022 on the Dragon datasets and benchmarks, and it was also an opportunity for me to collaborate with big teams of developers and researchers. I think this is all I have to say about this work, but if you have any specific questions about it, I can answer at any time.
Okay, thank you. Maybe a last question. So I was really interested by two of the future work you discussed. So one was on incentive. Okay, you already took it, I'm sorry. And one was how to evaluate the statistical heterogeneity. And okay, I think I guess there are a bit similar, at least. Because if you think, for example, to evaluate the value of a data set, I guess it's so clear that a very small data set, even a similar data set would be helpful for him, but if that's already a large data set, then heterogeneous variant will be good. So does your thesis maybe able to start like a framework where you could evaluate the importance of the data set? Maybe at the beginning of the training, one data set will be important, maybe at the end, one other will be important.
I will try to rephrase a bit your questions just to make sure that you understand. So what you are saying here is that we have this problem of quantifying statistical heterogeneity, and we also want to see the relationship with quantifying statistical heterogeneity with respect to participation, incentivization, and also maybe to the speed of convergence, because the importance of one distribution of one client to the other could vary with time because of where we are and where we are in the parameter space somehow. Okay. So I wanted first to start with another claim that is maybe not proven. And this claim is that quantifying statistical heterogeneity is as hard as collaboration, in the sense that in order for me to find out if another client is epsilon dissimilar from me, is equivalent for me to learning a good model in collaboration with this other client. And this is in fact due to the fact that I can, let's say that you want to estimate the difference between two distributions, and let's say that I have some sort of free divergence of or something similar to the discrepancy. Now my estimation of this quantity of this divergence will necessarily depend on my observations from each of those data distributions. And in fact, the sample complexity of my prediction will be the minimum between the two, the number of samples, the minimal number of samples across the two clients. So if myself, I have only few number of clients, samples. So if I only have a few number of samples, I can never be sure that I am very similar to this other client with a high probability, which is a bit a negative result, right? Because it is telling us that, oh, you cannot do anything in general. And in fact, this matches the first impossibility result which I was talking about, that collaboration is somehow impossible. I think that the same analysis can show that estimation statistical heterogeneity is impossible without having a structured model on the underlying data distributions. Now, this is one part of the question to the answer, just to show that already estimating statistical heterogeneity uniformly is hard. So somehow like having the discrepancy, which is the maximum difference of error across all the possible hypotheses. Now your question is even harder because I need to estimate the statistical heterogeneity at every point on the parameter space. Somehow I need a function that tells me that for this particular parameter choice, here is how the other client is far from you. And in reality, if you can't have access to this information, you have nothing private anymore because I know where the other objective function is at every place of the space. Which somehow is telling us that, okay, maybe you will have some oracle like this, which is already hard to estimate. But even if you have such an oracle, this is somehow telling us that you are no longer private because you know everything about the distribution. Somehow, if you have this information, you can reconstruct the underlying distribution, basically, or you can reconstruct the distribution of the risk function if you have access to this information. Which is a bit a negative result, but I think but this is like what I believe is the connection between quantifying statistical heterogeneity and the other aspect of the problem. A third point that I wanted to add is that I believe that quantifying statistical heterogeneity is the core problem here, because, for example, incentivization, and maybe here I am just saying some opinions that are mine, but maybe members of the jury may disagree. So some incentivization algorithms rely on the dissimilarity between clients to decide if to include some clients in the distribution or not. And somehow they are going in the direction you have mentioned it, that they need to know the difference between the clients at every point of the parameter space, which can be very restrictive. And if you can't get this quantity, of course, you can incentivize clients to participate. But otherwise, I believe that it will be very hard to incentivize clients to participate, for example. Again, this is a personal opinion, and maybe some other members of the jury may disagree with me. I mean, I don't know if this is the time to have a discussion about this, but
thanks a lot for your comments and answers. I think we'll stop here for the question of the jury. With the tradition to ask if the audience has a question, or do you for the PhD?
so who has a PhD here?
Okay, no question. So thank you, Othmane. So the jury will deliberate, and so we'll ask the audience to leave the room.
You can just sit out there with each other. No, yeah, you keep everyone out here. Just take him out of the
C'est pas nécessaire, c'est comme vous voyez. Je pense que c'est aussi